All right, kids, here we are with the partial pressure lecture and phase diagrams. Here is the lecture notes for partial pressure, and I don't even want to read them anymore because I don't know. I'm still not happy with it. But I'm going to freeze it here, or you can freeze it here for a minute and add in all the purple words to your notes if you would like. And basically, what I'm going to do is explain it with pictures. Here we go. My new favorite thing to show you. So what the partial pressure law says is that if we have a mixture of gases and we consider pressure to be collisions to the wall basically is causing this pressure of 6.74 atmosphere. And we have red and we have yellow gas, gas A and gas B, contributing to this total pressure of 6.74. So the Dalton's law of partial pressures basically says that the pressure being caused by the red balls and the pressure being caused by the yellow balls add up to be the pressure that is total. And we call those pressure, individual pressures, partial pressures. So the partial pressure of gas B, which is the red balls, plus the partial pressure of gas A, which is the yellow balls, combine to be the total pressure of the gas, which here is 6.74 atmospheres. This assumes that the volume and temperature stay constant, which isn't much to assume, as you know, anymore. So that is what all that says in purple words. So the total pressure is equal to the sum of the pressures that are making up the gas. And we call those pressures partial pressures. And when we do this, we have to make sure that the units match. You have to make sure all the partial pressures are in the same unit. You can't have kilopascals for one and atmospheres for the other. They all have to be the same. All right, so here is an example. And unfortunately, I have forgotten my magic pen. But that's all right, because you all can add, and I got this thing. Yeah. All right, so 3 gases in a container. Those 3 gases are hydrogen and oxygen and chlorine. And the total pressure of that mixture is 2 atmospheres. So 2 is the P total, and that's going to equal the sum of the partials. So the hydrogen partial pressure is 0.23, 0.23, and the and the chlorine partial pressure is 0.939. So 0.939, and we're trying to find the partial pressure of oxygen, 3.9, and then plus the partial pressure of oxygen will tell us that's the thing. So if we look at the one before, P total equals the sum of all the individuals, right? Individual pressures are adding into P total. So our P total here is 2 atmosphere. And so that's why it's 2. And then the partial pressure of hydrogen is 0.23. And the partial pressure of chlorine is 0.939. And then the PO2 is what we're looking for. So 0.23 plus let's see what happens. Let's keep that for now. 0.23. Woo, look at this. 0.23 plus 0.939. So the pressures that we know is 1.169, and then we subtract that number from 2. So to do that quickly, there I will do that and then add it to 2. And that'll give us, so 0.831 is what the partial pressure of oxygen is. And that's how you do it. All right, so I forget what I said, 0.832, I think. 0.832. 832. All right, that's what I get for forgetting my pen. Boy, these have really gone downhill, kids. I'm not going to lie to you. These were much higher quality at the beginning. All right, so the PO2 is equal to 0.832. All right, so here's the other one. Neon is collected over water at 25 degrees Celsius. The total pressure is 799.5 millimeters of mercury. What is it of dry neon? So what this is saying basically is we collect the gas by having a reaction, and then the gas bubbles in to water and collects up here. This is where the gas would collect. But the problem is, since we're doing this over water, there's some vapor, right? We know water causes vapor. That's why our showers get all steamy, and that's why it's so miserable to live here in the summer, because there's water vapor in the air. So this will be water vapor plus whatever gas it is we're bubbling out of our reaction. So the total pressure will be equal to the water. So P total. Ooh. I'm gonna be able to get some money, I think, from some unhappy people. All right, so the P total in this case is the partial pressure of the neon and the partial pressure of the water. And we were told what the partial pressure of the water was. The partial pressure of water was 23.7, and the partial total pressure actually was 799. Oof. That's some high quality writing right there. I can do Minecraft with that kind of look. All right, so 799 minus 23.7. This would be 799. This would be 23.7, and the difference between the two will give us a partial pressure neon. And just doing that in my head, that's 0.8, and 3 from 8 is 5. So it's 5.8. And then 2 from 9 is 7. So it's 775.8, I believe. That's what I believe. All right, so that's the partial pressure. That's the dry neon, the partial pressure neon. All right, so then we talked about phase diagrams, and phase diagrams look generally like this, where there's pressure on one axis and temperature on the other. And what this is supposed to tell us is where solid, liquids, and gases occur. And you can memorize it, certainly, because it's going to do the same pattern you'll see after we do a few of these. But you can also just think that when there's high pressure, this little area here, this area in this box, this area, we have high pressure and very low temperature. And if you just think of anything like water, what happens when there's high pressure and low temperature? Water is what phase? And hopefully you remember it is a solid. So this is the solid area. And then when you have high temperature, so over in this region here, and lower pressure, so collisions aren't as frequent, that would be a gas. So things are not as packed in together in the gas phase. So the pressure isn't as great, but the temperature is great because they're moving around pretty good. And then in between the solid and gas would be your liquid. So up here is your liquid area. So that is the area in here is liquid, and the area over here is gas. And so there's this other thing here. So this line here, and I'm going to try to change the color and really do the job. So this line here that I'm doing in green, not very well, but I'm doing it. Look at that. All right, so that line there is the line between solid and liquid. So this is where a solid would melt and a liquid would freeze. And actually on that line, you get both things existing. I know that's hard to believe, but it's true. If you go to 0 degrees in water, you would have partially liquid and partially solid water. And then I'll do it in blue. This area here is where a liquid is becoming a gas. So this line here represents where a liquid becomes a gas. And so you got boiling going one way, condensation going the other, and both liquid and gas exist there. That would be the boiling point. And that changes with pressure, and I'll show you that with my vacuum pump. So, and then here is where solid goes right to gas, and that might be familiar to you with dry ice, and I'll try to bring some of that in. But dry ice goes right to solid. Oh, brother, I swear, this is like kindergarten all over again. I can hear Miss Dungy now telling me I'm a good boy, and that's how I color. All right, so solid to gas, that is sublimation, I think is what we call that. Anyway, that's where it's going to happen right here. That is the solid to gas. Now, let's look at this a little closer. the points we need to know, the normal melting or freezing point, you'll see that right here. That's indicated by the point B. And the point B is the point at which, at atmospheric pressure, that the solid, remember this is the solid area here, this is the liquid area here, and this is the gas area here. So solid and liquid exist at atmospheric pressure, standard pressure, which is 1 atmosphere or 101 kilopascals or 760 millimeters of mercury. That would be the normal freezing or melting point. The normal boiling point on this graph, you can see, is indicated by the letter C, and that would be right here. And that is where liquid is turning to gas at atmospheric pressure, again, at standard atmospheric pressure. And the triple point is right here, point A. And point A is significant because that is the place where all three, solid, liquid, and gas, can exist. And I'll show you a video of that in a second. But before I do that, the critical point is way up here, this point E. And the critical point is the point on the graph where after which only a gas can exist. So there's so much temperature, so much mobility of those particles at this point that they can only act as a gas. There isn't enough pressure to bring them together to be a liquid or a solid anymore. So critical point, everything beyond, so off in here, that's always going to be a gas. That's the critical point. All right. The lines between the states, so as we talked about, like D to A or A to E, these lines, the two phases exist. And so this line here between A and D is the line between which solid and liquid both exist. And this line here between A and E is where liquid and gas both exist. All right, so let me show you that video real quick. I'm going to discard that, I guess. I'm going to do that. And here we go. Let's see this. So this video shows you a triple point, and this is cyclohexane. And cyclohexane is going to solid here, and then after it turns to a solid, it's boiling as a liquid. So that's both so that's the boiling point, and then it's the freezing point, and then it's the melting point, and then it's the freezing point. So if you want to watch this video in full, I've put it on the line. But as you can see, you got solid, and then you got liquid boiling, and then that liquid freezes again. And the reason for this we'll go over, I guess, next unit in full. But they talk about how it takes energy to make something boil, and that energy comes from the room, and as a result of losing that energy, the flask freezes, etc., etc. All right, so that's another look at fight, and that's it, I guess. That's it. So there it is, the rest of the unit. Enjoy. I'll talk to you later.